You know how a spinning top just stays up, kind of defying gravity? Or how a rolling coin can carve out a perfect circle? Well, the physics behind that is exactly what we're going to tackle today with this classic rolling cone problem. This isn't just some textbook exercise. It's a really cool puzzle that, once you solve it, gives you a whole new way of seeing how things spin.
Okay, so picture this. A cone is rolling on a surface, and it's tracing a perfect circle. It's almost magical, right? Like it's stuck on some invisible track. But there's no string, there's no guide rail, so what's keeping it in that circle? What's the invisible force that's steering it and keeping it from just toppling over or sliding away? That's the big mystery we're here to solve.
All right, so before we jump into any equations, the first thing we've got to do is just understand the problem. Let's break down exactly what the cone is doing piece by piece so we know what we're dealing with. Okay, so here are the givens, the stuff we know. We've got the cone's mass, its half angle, which is basically how steep it is, and the location of its center of gravity. We're also told the friction coefficient, how grippy the surfaces are. And what we need to find is twofold. First, for a specific angular speed, what's the friction force? And second, what's the range of speeds, the sweet spot, where this cone can roll without any slipping at all? So, before we can actually solve this, we need to make sure we've got the right tools in our physics toolkit. Let's just quickly review the fundamental ideas we're going to be using. First up, torque. And the best way to think about torque is just opening a door. You push on the handle, as far from the hinge as possible, right? You don't push right next to the hinge. That's because you're applying a twisting force. And that's all torque is. It's the rotational equivalent of a force. If you want to change an object's rotation, you need to apply a torque. Next, we've got static friction. And honestly, this is kind of the unsung hero of this whole problem. Think about pushing a really heavy box. At first, it won't budge. Why? Because static friction is pushing back against you, matching your force exactly. But it's not infinitely strong. It has a maximum limit. Push harder than that limit, and poof, the box slides. That breaking point is going to be absolutely crucial for the second part of our problem. And here it is, the big one, the master equation for rotational dynamics. Now, I know it looks a little intimidating, but don't worry. All this is really is the rotational version of Newton's second law, F equals ma. It's just saying that the net external torque, that's the N, is equal to the rate of change of the angular momentum, the m. This is the equation that's going to let us connect the forces we see to the motion of the cone.
Okay, we've got our tools, we've got our concepts. Let's start solving. We'll begin with part A, finding that static friction force for a specific angular speed. So, first things first, before we write down any equations, just take a second and visualize it. What forces are actually acting on our cone? I mean, really think about it. You've got gravity, right? Pulling it down. You've got the normal force from the surface pushing up. And of course, the one we're really interested in, friction. Now let's see how these all play together. So here's our game plan. It's a 4-step process. Step 1, we're going to analyze the forces, paying attention to vertical balance and horizontal acceleration. Step 2, we'll calculate the torque produced by friction. Step 3, we'll figure out how the cone's angular momentum is changing. And finally, step 4, we'll use that master equation to link everything together. It's a clear path to the answer. Okay, and right here, I want to call out a super common pitfall, a trap that a lot of people fall into. You might think the normal force, N, is just equal to the weight, mg. But it's not. You have to remember the friction force is acting along the slanted surface, so it has a vertical component too. That means the normal force has to support the weight and fight against that downward part of the friction. It's a subtle point, but it's absolutely crucial to get it right. And here's the real heart of the problem. This is the cool part. The cone has angular momentum because it's spinning, but that whole axis of rotation is itself rotating in a big circle. That wobble is what we call precession. Now, for the angular momentum vector to be constantly changing direction like that, to be precessing, you must have an external torque. And what's the only force that can provide that torque about the center of gravity? You got it. It's the static friction. So, once we work through the algebra, we set up our force equations, we calculate the rate of change of angular momentum, we set that equal to the torque from friction, we can finally plug in the numbers from the problem. And when we do that, we find that the friction force needed is 0.8 newtons. And that's our answer for part A. All right, part A is done. We know the friction for one specific speed, but now for the really interesting part B. We're going to figure out the entire operating window. What are the minimum and maximum speeds the cone can roll at before it starts to slip? The whole key to this part of the problem comes down to one simple inequality. Remember how static friction has a maximum value? Well, for the cone to roll without slipping, the friction force that's required for the motion has to be less than or equal to the maximum friction that's available. As long as that condition holds, we're golden. The second it's violated, the cone slips.
Now, this is what makes the problem so cool. There's not just a maximum speed, there's a minimum one, too. Think about it. If the cone rolls too slowly, what happens? Gravity kind of takes over and it wants to slide down the incline, inwards. So friction has to point up the incline to prevent that. But if you spin it too fast, the centripetal effects take over and it wants to fly up the incline, outwards. Now friction has to point down the incline to hold it back. So friction completely reverses its role depending on the speed. So our strategy is simple. We're going to find those two edge cases. We'll set the required friction equal to its maximum possible value, k times n. We'll do it once for the too slow case, where friction points up the incline. That'll give us our minimum omega. Then we'll do it again for the too fast case, where friction points down, and that'll give us our maximum omega. And when we run the numbers for those two scenarios, here's the window we get. We find the minimum angular velocity is 0.8 radians per second. Any slower, and it slides down. The maximum is 2.8 radians per second. Any faster, and it slides up. So as long as the cone's angular velocity is between those two values, it will roll perfectly without slipping.
So, there you have it. We've cracked the problem. But let's take a step back from the numbers and think about the big picture. What are the really important physics concepts we used here?
Well, first, we saw just how reactive static friction is. It's not a constant force. It adjusts its direction and its size to meet the demands of the situation. Second, and this is huge, we saw that torque is what changes angular momentum, and that's the key to understanding why things like tops and our cone precess. Third, it's a great reminder that even a problem that looks really intimidating can be solved if you just break it down into a logical, step-by-step approach. And finally, it really drives home that every single term in these equations, it's not just math. It's describing a real physical thing that's happening. And just to leave you with something to chew on, how would all of this change if our cone were hollow instead of solid? Think about it. The mass is the same, but its distribution is totally different. So how would that affect its angular momentum? And how would that, in turn, change our no-slip window? It's a great follow-up question. Give it some thought. Thanks for joining me.